Welcome to the Vitality Equation, exploring research in health and well-being one paper at a time.
All right, everyone. So today we're diving into some pretty interesting research. This one's titled XpressO-Melanoma, an explainable deep learning model for the prediction of BRAF V600 mutation status in cutaneous melanomas. Big title, lots of science.
Sounds complex. Cutaneous melanomas, that's skin cancer, right? And BRAF V600 mutation, that's got to be some kind of genetic thing going on.
Exactly. It's a specific mutation in a gene called BRAF. This mutation is found in a significant percentage of melanomas, and it's actually a key target for certain cancer therapies. So knowing whether or not a patient has this mutation is super important for deciding on the right treatment plan.
Okay, so the paper is about predicting whether or not the mutation is present. Why is that important? I mean, can't they just test for it directly?
That's where the explainable deep learning model part comes in, I think. Traditional biopsies and genetic testing can take time, right? And they're invasive. This model, from what I gather, uses images like pictures of the melanoma to predict the mutation status.
Yes, and potentially speed up the process. The explainable part is really key. Deep learning models can be like black boxes. They give you an answer, but you don't always know why they gave you that answer. This research focuses on making the model's reasoning transparent, which is crucial for doctors to trust it.
Transparency is huge. It's not just about trusting the model, it's about understanding how it's making decisions. That understanding can potentially lead to new insights about the disease itself. If the model is consistently focusing on certain visual features of the melanoma to predict the mutation, that tells us something important about the underlying biology.
It could highlight visual markers that doctors might not even be consciously aware of. Okay, so how could this impact people's lives practically, day to day?
Well, imagine you go to the dermatologist with a suspicious mole. Instead of immediately scheduling a biopsy and waiting weeks for results, they could take a picture of the mole and run it through this model. If the model predicts a high likelihood of the BRF mutation, that could expedite the process of getting you the right treatment. Take it expedite also can help to avoid unnecessary invasive procedures.
And think about the anxiety reduction. Waiting for biopsy results is incredibly stressful. Even a preliminary prediction could help people manage their expectations and start mentally preparing for the next steps. It is all about understanding the reality that faces you and starting from that point.
Yes, and on the flip side, if the model predicts a low likelihood of the mutation, it could prevent unnecessary biopsies and the associated anxiety. It's like a pre-screening tool.
Exactly. And it's not just about speed and convenience. In areas where access to specialized dermatologists and genetic testing is limited, this could be a game changer. A general practitioner could use the model to make more informed decisions about referrals.
Okay, I'm seeing the potential benefits. But let's dig a little deeper into the explainable part. How exactly do they make the model transparent? What are the specific techniques they use?
From what I understand, they're using techniques like attention maps or saliency maps. Basically, these maps highlight the specific regions of the image that the model is focusing on when making its prediction. So, it's not just saying yes, mutation likely, or no, mutation unlikely, it's showing where in the image it saw the evidence.
Right. It's like the model is pointing and saying, I'm focusing on this area here because it has these specific characteristics, and that allows doctors to evaluate whether or not the model's reasoning makes sense from a medical perspective. It also provides some insight into what exactly the model is doing.
That makes a lot of sense. So, if the attention map highlights an area with irregular borders, that might be a feature that doctors already know is associated with melanoma. But if it highlights something completely unexpected, that could be a new discovery waiting to happen.
Yes, and it's not just about visual features. The model might also be picking up on subtle textual differences that are invisible to the naked eye. That's where the real power of deep learning comes in, its ability to identify patterns that humans can't.
This reminds me of some research I was reading about how environmental conditions affect plant evolution. The way plants adapt to stress, drought, sunlight, whatever, leaves these telltale markers. It's not visual like melanoma, but seeing this deep learning model pick up on visual markers in the same way makes me wonder if we can apply similar principles to ourselves. Can we see visual health markers in our own environment that affect our well-being if we apply enough focus?
That's a really interesting parallel. It speaks to the underlying principle of pattern recognition, whether it's in a plant, a skin cell, or even our own cognitive processes. I mean, in CBT, we're constantly looking for patterns in people's thoughts and behaviors, trying to identify the triggers and the maladaptive responses. This is really neat to relate the science of computers with the science of life and the natural environment.
Right, and I was reading about how seed dispersal strategies in plants relate to energy expenditure. The way a seed travels and establishes itself is so connected to its environment. It makes me wonder if we can apply that same concept to our own physical routines and energy levels. Maybe we need a deep learning model for our own bodies, helping us optimize our activity based on the environment we're in, our stress levels, sleep quality, diet, etc. Could this model tell us to do something? Should we run or do yoga today?
That's a fascinating idea. It's almost like creating a personalized cognitive behavioral map of your life, identifying the specific activities and practices that are most effective for you in different situations. I can see this becoming useful, especially when it comes to personalized treatments. It is much easier for me to run when the weather is nice, but maybe I should run when it is raining. It would be hard to think about and implement otherwise.
And you could integrate mindfulness techniques into that. The model could flag times when you're experiencing high stress and recommend specific meditations or mindful movement practices to help regulate your response. It's not just about reacting to stress, it's about building resilience beforehand, which interestingly is what the researchers studying plant resilience focus on.
Yes, and you could track sleep quality and see how it correlates with the model's recommendations. If you're consistently sleeping poorly after doing high-intensity exercise, the model might suggest switching to a more restorative activity like yoga or stretching in the evening. That is a simple application of personalized optimization. It can be a lifestyle.
It's all about feedback loops, right? The model provides insights, you adjust your behavior, and then you see how those adjustments affect your overall well-being. It's like a continuous cycle of learning and optimization, both for the individual and for the model itself.
Mhm. And that ties back to the explainable part of the melanoma model. If the model is transparent about its reasoning, you're more likely to trust its recommendations and actually implement them. If it just says do yoga, you might dismiss it. But if it says do yoga because your heart rate variability is low and your stress hormones are elevated, you're more likely to take it seriously.
Yeah, it needs to connect the dots for you. Okay, so getting back to the melanoma research, what are some of the limitations of this model? I mean, it's not going to replace biopsies anytime soon, right?
Of course not. It's important to remember that this is a prediction, not a diagnosis. The model is only as good as the data it's trained on. If the training data is biased, for example, if it primarily includes images of melanomas from one skin type, then the model might not perform as well on other skin types.
And image quality is a factor too. If the images are blurry or poorly lit, the model might struggle to identify the relevant features. It is also possible that the model isn't accounting for the history of the melanoma. Did they use sunscreen a lot or not?
Yeah, and there's always the risk of overfitting. That's when the model becomes too specialized to the training data and loses its ability to generalize to new, unseen data. It is super important not to over-specialize for a given group.
Exactly. Overfitting is a common problem in deep learning, and it's something that researchers need to be very careful about. They need to use techniques like cross-validation to ensure that the model is robust and can perform well on a variety of different images.
So the next step would be to validate this model on a much larger and more diverse data set, and ideally to test it in a real-world clinical setting, comparing its performance to that of experienced dermatologists.
Yeah, a head-to-head comparison would be really interesting. See how the model performs compared to human experts. And also to see how the model's explanations influence the doctor's decision-making process.
That's a great point. It's not just about whether the model is accurate, it's about how it can augment human intelligence. Can the model help doctors make better decisions, even when they disagree with its prediction? That's the ultimate goal.
It's kind of like how I use meditation. I don't expect it to solve all my problems, but it helps me to see things more clearly and make better choices. This model could be a similar tool for dermatologists, helping them to approach each case with more information and a fresh perspective.
Yeah, it's not about replacing human expertise, it's about enhancing it and about providing access to care in areas where there may be doctor shortages. Okay, so thinking about future research directions, what are some of the most promising avenues to explore?
From a cognitive perspective, I'd be really interested in seeing how these models can be used to identify new visual biomarkers for melanoma. If the model is consistently focusing on features that doctors haven't traditionally considered, that could lead to new insights about the disease and how it develops. Also, does the introduction of AI into the diagnosis change how doctors are thinking? Is it introducing new biases or other changes?
And from my perspective, I'd love to see research on how these models can be integrated into patient education and empowerment. Could patients use these models to monitor their own moles and identify potential problems early on? Or could the model's explanations be used to help patients better understand their diagnosis and treatment options?
And I'd be curious to see how these models can be used to personalize treatment plans. Could the model predict how a patient is likely to respond to different therapies based on the visual characteristics of their melanoma? That could help doctors to choose the most effective treatment from the start, which is important.
Personalized treatment plans are the way to go in the future. It makes sense that even at the cellular level things can be personalized. Great. I think we've covered a lot of ground on this one. It's a fascinating example of how deep learning can be used to improve healthcare.
Definitely. And it highlights the importance of transparency and explainability in AI. It's not enough for a model to be accurate. It also needs to be understandable and trustworthy.
Absolutely. So that's it for this episode of the Vitality Equation. Thanks for tuning in, and we'll see you next time.